Hi there, this is the second video about conditional probability, and I promise this one will be shorter than the previous one. We're just going to go through a couple of examples to see what we can find out. So, when you're given a conditional probability question, you could be asked to interpret a Venn diagram or a Carnot map, or you could be just given some probabilities and asked to calculate a conditional probability statement. Remember, the key word for conditional probability is given. It's not always there, but it frequently is. Let's have a look at this first example. Two dice are rolled and the outcome is observed. Given that both numbers add up to 7, there you go, there's the key word, given. What's the probability that dice faces are 4 and 3? So remember I talked about in conditional probability the concept of restricting the sample space. So when you roll two dice, the sample space is classically 36, right? 6 times 6, 36 different possibilities. But I'm given that both numbers add up to 7. My sample space is just here. Did I say this before? I'm going to do this in two different ways, so you can sort of see how it's done from a conceptual point of view, and then how the probability calculation will get you to the same point using a formula. So here are the possibilities: 1, 6, 2, 5, 3, 4, and then 4, 3, 5, 2, 6, 1. Remember that this outcome is different from this one because this is a 1 on the first die and a 6 on the second, and this is a 6 on the first die and a 1 on the second. So although they give you the same look, I suppose, imagine if the dice were different colors, they're different outcomes. Okay, so I'll just use this squiggle here to say a 4 or a 3 in the most simplest way possible. So what's the probability of a 4 or a 3 on a die, given that it's a 7? Well, the possible outcomes are 1, 2, 3, 4, 5. There are 6 possible outcomes that give me a 7. So that becomes my bottom number. My top number is the matching outcomes, and I'll use a different color to see that. It says the dice faces are a 4 and a 3. So there's a 4 and a 3 there, and there's a 4 and a 3 there. So assuming order doesn't matter, I suppose. So there are two ways of getting a 4 and a 3, or 4 or a 3 on your dice. And we can simplify that to 1/3, and we're done. Okay, it does require you to list all those possible outcomes. Make sure you get all the possible outcomes right before getting your final answer. Now let's have a look at it from the probability formula perspective. And just to remind you, the probability formula is probably, oh, I've got it down there actually. I'll just point here. The probability of A given B is equal to the probability of A and B, or intersect B, over the probability of B. So this assumes that you've got some calculations happening already. So in this case, we've got probability of a 4 and a 3 and getting a 7 on the dice. So without drawing a table, because it's so common, I'm hoping me just verbalizing it's enough. If you can imagine your table of a 6 by 6 column, 6 columns by 6 rows down here, then it's that middle diagonal which would give you all the possible 7s. So that means that there are 7 possibilities there, 2 of which are a 4 and a 3. So we end up with 2 out of 36. Note the 36 because we're looking at the big sample space. So we've got 2 out of 36 would be a 4 and a 3 and a 7 over the probability of a 7. And the probability of a 7 is 6 out of 36. So from our probability calculations, we get this. Now remember that between here and here, we can just divide top by bottom by that big bar. So that's equal to 2 out of 36. And I'm going to change and flip, right? So the divide becomes a times. Should be a 36 there. And then I'm going to go 36 over 6 here. So I've just multiplied by the reciprocal. Now I can cancel down the 36's top and bottom. This always happens with this kind of problem. And then I can see I've got left 2 on top and 6 on the bottom, which is equal to 1/3. So you can see from this point here, I've really got the same as this. The difference between the two is I didn't really have to consider the sample space. But, I feel like this solution 1 seemed a little bit faster. So let's have a look at example 2, where we're not given the sample space, but we're just given a whole set of probabilities. So the probability of A is 0.3, the probability of B is 0.4, and the probability of A given B is 0.6. And we're asked to work out what the probability of B given A is. It's not the same. So you can't just flip the A and the B around. So we need to be able to work out a few things. We know that the probability of B given A which is what we're looking for, is given by the probability of B intersect A, which we don't have yet, we don't know what it is, over the probability of A, which we do have, it's 0.4. Great. But we don't have the probability of B given A. However, we do have one more fact, and that is that the probability of A given B is 0.6. So that means we also know this. I'll choose a different color just so I can sort of highlight. We know A given B because we're given it. We know the probability of B because we're given it, which means that we can work out this probability of A and B. And maybe now you might appreciate why I went to some pains before to explain how A intersect B is the same as B intersect A in the previous video. These are two equal things. That means that the probability of B intersect A is the same as the probability of A intersect B, which we can now work out. Let's put it all together really quickly. So the probability, I'll change my colors there. The probability of A given B is equal to the probability of A intersect B over the probability of B, which equals, well, A intersect B we don't know. The probability of B we do know, it's equal to 0.4. And we know that that's equal to the probability of A given B, which we also know, 0.6. So we can work out the probability of A and B, or intersect B, is equal to 0.6 multiplied by 0.4, which is going to be 0.24. And that's the probability of B intersect A. Okay, great. That's half our effort done. So now the probability of B given A is going to be the probability of B intersect A over the probability of A, which is equal to, well, we know what B intersect A is now because we just worked it out. It's 0.24. And the probability of A we've worked out, and it's 0.4. Oh, sorry, it's 0.3. So 0.4 divided by 0.3, 0.24 divided by 0.3 is going to be 0.8. I hope my mathematics is right there. You can check on your calculator yourself. So that's it. That's the calculation done. So what is the probability of event B happening given that probability of A has happened? Well, there's an 80% chance, 0.8. And that's how you do it. Have a go at some of the work from your textbook, and I'll see you next video.